Hello viewers, in this part of the program, I am going to discuss the measurement of irrigation water. Irrigation water is very important input for crop production. Accurate measurement of irrigation water is necessary for its most intelligent use. Measurement of irrigation water is also necessary for its distribution among the users. Water is the most valuable asset of irrigated agriculture. Accurate measurement of irrigation water permits more intelligent use of this valuable natural resource. Such a measurement allows the water to be distributed among users according to their needs and rights. Systematic water measurements, properly recorded, interpreted, and used constitute the foundation upon which increasing efficiencies of water conveyance, application, and use must be based. Accuracy in water measurement is therefore of prime importance in the operation of any water distribution system. Methods of water measurement. Several devices are commonly used for measuring irrigation water on the farm. They can be grouped into four categories: volumetric measurement, velocity area method, measuring structures like orifices, weirs and flumes, and the tracer method, that is also called as dilution method. So, these different methods are being used for measuring irrigation water, and the particular method used for measuring water depends upon the accuracy of that method and the equipments or facilities available. Volume method of irrigation water measurement. A simple method of measuring small irrigation streams is to collect the flow in a container of known volume for a measured period of time. An ordinary bucket or barrel is used as the container. The time required to fill the container is reckoned with a stopwatch or the second hand of a wristwatch. The rate of flow is measured by the formula: discharge rate in liters per second is equal to volume of container in liters divided by time required to fill in seconds. This method is very simple and it is very easy, and in hydraulic laboratories this method is used for calibrating of other devices. For example, if a 24-liter capacity bucket is filled in 12 seconds by the discharge from a Persian wheel, then the rate of flow is 2 liters per second or 120 liters per minute. The method can be used to determine the discharge rate of pumps and other water lifts like Persian wheel and leather bucket lift, that is Chadas. If a barrel of 150 to 200 liters capacity is used to collect the flow. The method is frequently used in hydraulic laboratories for calibrating other devices and instruments used for measuring flow. The another method of water measurement is velocity area method. The rate of flow passing a point in a pipe or open channel is determined by multiplying the cross-sectional area of the flow section at right angles to the direction of flow by the average velocity of water. Discharge is equal to area into velocity, or Q is equal to A into V, in which Q is discharge rate in cubic meter per second, A is area of cross section of channel or pipe in square meter, and V is the velocity of flow in meter per second. The cross sectional area is determined by direct measurements. The velocity is generally measured with a current meter or by float method. The velocity is determined by current meter if the more accuracy is required, or it may be determined by float method if less accuracy is required. Float method. It is the simplest and cheapest method to measure the approximate discharge, that is velocity, in an open channel of non-cross section. A block of wood may be used as the float. A straight uniform section of the stream about 30 meter long is selected, and the time required for a float carried by the stream to traverse the marked distance is measured. Since the velocity of the float on the surface of water will be greater than the average velocity of the stream, therefore, a constant factor of 0.85 is multiplied to obtain average velocity of the stream. A piece of wood or a half-filled long neck bottle is used as float. It is kept in mind that the channel should be straight, that is used for measurement of the velocity by float method. And since the velocity of water at the surface is less in comparison to the velocity of water at deeper layers, therefore, the factor 0.85 is used to multiply for the average velocity of water by the float method. Current meters. The velocity of water in a stream or river may be measured more accurately with a current meter. Current meters usually consist of a set of cups, that is cup type, or propellers, that is propeller type, that rotate about a vertical axis when placed in flowing water. Rate of rotation of cups can be indicated and recorded electrically. The number of revolutions of the wheel in a given time interval is obtained, and the corresponding velocity is reckoned from a calibration table or graph of the instrument. So, the current meters are used when more accuracy is required, and again it is kept in mind that the current meters are placed between the stream. It should not be kept above side of the stream or lower side of the stream. Measuring structures. The most commonly used devices for measuring water are weirs, partial flumes, orifices, and meter gates. In these devices, the rate of flow is measured directly by making a reading on a scale which is a part of the instrument and computing the discharge rate from standard formulas. The discharge rate can also be obtained from standard tables or calibration curves prepared especially for the instrument. All these devices can be made locally for farm use and give accurate results when constructed, installed, and operated properly. The choice between one or the other depends on the expected flow rates and site conditions. The use of weirs, partial flumes, and orifices depend on the stream size and site characteristics, and as per the suitability, these devices may be used for measurement of irrigation water. Weirs. Weirs are used to measure flow in an irrigation channel or the discharge of a well or canal outlet at the source. A weir is a notch of regular form through which the irrigation stream is made to flow. The notch may be rectangular, trapezoidal, or triangular. Rectangular weirs and 90-degree V-notch weirs are commonly used on the farm. The discharge through a weir notch is proportional to the head on the crest and is affected by the condition of the crest, the contraction, the velocity of approaching stream, and the elevation of the water surface downstream from the weir. Weirs are generally used for varying stream sizes. These are used for small as well as large streams. Basic formula for calculating discharge through a weir is Q is equal to C into L into H raised to power m, in which L is the length of crest in centimeter, H is the head on crest in centimeter, C is a coefficient dependent on the nature of the crest and approach conditions, and m is an exponent depending upon the weir openings. The weir, when properly constructed and installed, is one of the simplest and most accurate devices for measuring irrigation water. Weirs are unsuitable for water carrying silt which deposits in the approach channel and destroys the proper conditions for weir measurement. They require considerable loss of head, often not available in channels on flat grades. Therefore, there are two disadvantages with weirs for measurement of irrigation water. The first disadvantage is that weirs do not give accurate measurement when the water is laden with silt or sand. The second disadvantage is that the considerable loss in head is required for weirs in the channels. The three types of weirs have been shown in this figure: rectangular weirs, trapezoidal weirs and V-notch weirs. Rectangular weirs are suitable for measurement of large stream. Trapezoidal weirs are suitable for measurement of medium streams, whereas V-notch weirs are suitable for measurement of medium and small streams. Flumes. More accurate measurement of flow with silt laden water can be obtained with flumes. The flume is formed by side contractions in the channel. These are specially shaped sections of channels that are set into the bed for measuring flow of water. The principle of flumes is based on the concept of specific energy and critical flow in open channels. So, there is disadvantage with flumes. They can give accurate measurement of the silt laden water, whereas weirs do not give accurate measurement of silt laden water. Partial flume. The partial flume is an open channel type measuring device that operates with a small drop in head. It is a self cleaning device. Sand or silt in the flowing water does not affect its operation or accuracy. The floor of the upstream section of the flume is level and the walls converge toward the throat section. The walls of the throat section are parallel and the floor is inclined downward. The walls of the downstream section diverge toward the outlet and the floor is inclined upward. Small flumes are made of sheet metal while large ones are made of concrete. The size of the flume is determined by the width of its throat. Partial flumes, there is advantage that there is self cleaning device and the varying discharges can be measured with the help of partial flumes depending upon the width of the throat. Whenever large measurements are needed, wide throat partial flumes are used. Whenever small stream is to be measured, then narrow throat partial flumes are being used. Discharge through the flume can occur under either free flow or submerged flow conditions, where the elevation of the water surface downstream from the flume is high enough to retard the rate of discharge. The flow is considered submerged. To determine the discharge, two scales HA and HB are provided at the upstream and downstream sections of the flume. Only HA needs to be measured under free flow conditions. This is the view of partial flume. There are three sections in this partial flume, that is converging section, throat and diverging section. The walls of partial flume in converging section converge towards the throat. The walls of partial flume in throat section remains parallel and the walls of partial flume in diverging section diverge towards the channel. As well as the floor position is different in three different sections. The floor of partial flume in diverging section remains flat. The floor of partial flume in throat section inclined downwards. The floor of partial plume in converging section remains inclined upward. So, the fabrication of partial plume is little bit complicated, but the fabrication of partial plume facilitates the self cleaning, and there are two scales for measurement of water, HA and HB. HA scale remains in converging section and HB scale remains in throat section towards diverging section. Whenever there is free flow, then the reading of HA is sufficient and the discharge is computed from the help of tables. When there is submerged flow, the reading of HA and HB both scales are needed, and in this case the flow towards downward becomes more, and this more flow towards downward retard the flow on upstream sides. Cut throat plume. It has a flat bottom, vertical walls and a zero length throat section. Since it has no throat section, it was given the name cut throat. The most obvious advantage of a cut throat plume is economy, since fabrication is facilitated by a flat bottom and removal of the throat section. This is the additional advantage with cut throat plume, that its fabrication is less complicated in comparison to partial plume, and the cost involved in fabrication of cut throat plume is less in comparison to cost involved in fabrication of partial plume. It is easy to measure water with cut throat plume. The cut throat plume can operate either as a free or a submerged flow structure. Under free flow conditions, critical depth occur in the vicinity of minimum width W, which is called the plume throat or the plume neck. When the downstream flow depth become greater than critical depth, resulting in a change in the upstream depth, the plume is operating under submerged flow conditions. This is the view of cut throat plume. Here there are only two sections, converging section and diverging section, and neck is there between these two sections. The width of the neck is important. When the depth of upstream flow is equal to width of the neck, then it is free flow. But when the depth of the water in diverging section becomes more than the width of the neck, then the flow is submerged. And under submerged flow conditions, again two measurements are required, HA measurement and HB measurement. Just like partial plumes, there are two scales in cut throat plume. One scale is in converging section and another scale is in diverging section. Under free flow conditions, the HB scale is being used, and under submerged condition, HA and HB both scales are used for computation of discharge. Orifices. Orifices in open channels are usually circular or rectangular openings in vertical bulkhead through which water flows. The edges of the openings are sharp and often constructed of metal. The cross-sectional area of the orifice is small in relation to stream cross-section. These conditions allow complete contraction of the stream flow and the velocity of approach becomes negligible. Orifices are generally used for measurement of small streams. In orifices, the diameter of orifice is always less than the cross-sectional area of the stream. Orifices may operate under free flow or submerged flow conditions. Under free flow conditions, the flow from the orifice discharges entirely into air. In submerged flow orifices, the downstream water level is above the top of the opening and the flow discharges into water. Submerged orifices can be conveniently used for measuring small discharges. They do not require a fall in the level of the bed of the channels as is required in the case of weirs. Discharge through orifice is given by the equation Q is equal to C into 10 raised to power minus 3 into A into under root 2GH, where Q is discharge in liters per second, A is orifice area in square centimeter, G is acceleration due to gravity in centimeter per second, H is head of water causing the flow in centimeter, and C is coefficient. Submerged orifices have the disadvantage of collecting floating debris, sand and silt above the orifice, preventing accurate measurement. Orifices may be used where fall of the water is less, whereas in case of weirs, when the fall of water is more, only then weirs can be used. Free flow orifice plates can be used to measure comparatively small streams like the flow into boulder strips, furrows or check basins. Different type of weirs have been shown in this figure. When the inlet is at higher level, when the inlet is at lower level. The view of submerged orifice is also shown where the downstream level is lower in comparison to upstream level. Another method of measurement of water is tracer method. This method is also known as dilution method. The tracer method of water measurement are independent of stream cross section and are suitable for field measurement without installing fixed structures. In these methods, a substance, that is tracer, in concentrated form is introduced into the flowing water and allowed thoroughly mix. The concentration of the tracer is measured at a downstream section. Since only the quantity of water necessary to accomplish the dilution is involved, there is no need to measure velocity, depth, head, cross sectional area or any other hydraulic factors usually considered in discharge measurements. These methods are simple and no fixed structures are required for measurement of water in these methods. Only water is needed for dilution, and on the basis of dilution the actual discharge of water is calculated. In salt dilution method, non-concentration solution of common salt or dye is introduced into the flow at a known rate and its concentration measured downstream. Radioisotope method can be used in place of salts or dyes. Instead of concentration of salts, gamma ray emissions are recorded. A known amount of radioisotope is introduced into the flow and the counts recorded downstream by Geiger counters or scintillation counters. So, both salts or dyes or radioisotopes may be used in dilution methods, and at the point where there is sufficient dilution, the sample is taken and dilution is determined, and ultimately discharge is determined by this method. In this part of program, we have discussed the measurement of irrigation water. Measurement of irrigation water is important from the point of view of its scientific use. Various devices and methods are used for measurement of water. Water may be measured volumetric or by the area velocity method. Various devices like weirs, orifices and flumes may be used for measurement of water. Dilution method is also used for measurement of irrigation water.